So now we're going to move to another kind of motion called uniform motion. All right, so this is now getting a little bit more real. We take Hal, and he moves with a constant rate like that. Okay, we're not going to try to do this with a lab partner. It happens too fast. But just visualize Hal moving along. Pretend Hal is not rolling. It's really rolling, but just pretend that it's gliding. So the first step is to draw it, right? So here's our track. It's not going anywhere. Hal was here, and he moves here. So you can see sort of the importance of displacement. Right? Hal is constantly going through displacement. So let's start with the graph. Let's see, I think I'll put the graph, I'll cram it in here. I meant to give myself a little more room than that. I'll put the graph over here. Sneak the graph right here. In your notes, you can put it under there. So, graph. We're still doing a position time graph, right? So, I'm still going to put time there in seconds, we'll say. And I'm going to put position here, x, in the x position in centimeters, like that. Okay? And we're going to think about how, again, we'll do 0, 5, 10, and 15 seconds. And we'll think, where is Hal? So if we're doing this for real, you'd have an axis and you'd know everything. So let's imagine, though, that I started him not at 0, but at 20, and that I moved him in such a way he's moving so much per second. Now just imagine that motion, and let's make the plot. At time equals 0, it wasn't at the origin. He actually already had some displacement. He had what we'd call an initial position. Right? And then about 5 seconds later, so say that was 20, 5 seconds later, he's up to 40. Right? And if it's uniform motion, that means it doesn't speed up or slow down. I forgot to define it. Moving in a straight line, not speeding up or slowing. Leave off that preposition there. So at 20, at time equals 0, he's at 20. You wait 5 seconds, suddenly he's at 40. You wait 5 more seconds, and suddenly you find that he's at 60. Right? Whoa, that's a line. And then you wait 5 more seconds, and suddenly there he is at 80. All right, so we made a line. 80 here. Right. So if you were to track Hal's motion in uniform motion, if you were to track it with a position time plot, right? So that's what we're thinking about now. Position time plot, you'd get a line, right? It won't be flat like in the motionless case, but it would be a straight line, okay? So what we would say about Hal, we would describe him, is we'd say Hal has velocity, okay? So velocity is the ratio of the displacement between two times, this is kind of a long definition, between two times over the time difference. Over the time difference. Okay? That's what velocity means. And you can see we're showing it graphically here. This thing has velocity. So now let's do the equation, right? There's the graph, and here's the equation that we would do. And it looks like this. How many know what symbol that is? I'm worried you don't. Do they teach cursive anymore? Does anybody learn cursive anymore? A few of you learn cursive. I don't think they teach cursive. My poor 16-year-old is getting old enough he has to sign forms. And it says print your name, and he prints his name, and it says sign your name, and he prints his name. So it's a little bit, because they never learn cursive. And my dad learned cursive. Look at this. Look at that. 1980. Look at that cursive. I was in 4th grade, and I wrote that beautiful cursive. Do you know why I still have this? Are you kidding me? Look at that! I was 9. I was 9. That just wrecked my 4th grade GPA. It was just total trouble. I never got into med school because of that, VX. Now I've got to teach this garbage. Okay, so VX, delta x over delta t. Okay, that's exactly what the words say. It's the ratio of the displacement between two times over the time difference. So if you remember back what delta x is, the displacement, it was x final minus initial, but now we're going to start switching notation on you. You got to get used to that in physics. Instead of initial and final, I'm going to put 1 and 2, right? From time 1 to time 2. We'll even put it up here, right? So x2, the final position, minus x1, the initial position. And for a time difference, you'd put the same thing. You'd say it's the t2 minus t1. So what you're saying here is it's at x1 at time 1, and it's at x2 at time 2. That's all that means. Right? And you may think, oh, I've done algebra, I know what this is, or whatever. You'd say this is the slope of the xt graph. Right? That's all that is. So the velocity, there's several ways you can think about it, right? It's the displacement over the time, or it's this slope equals the velocity. Right, the velocity, right? Okay, now, for a practice problem, I want you to, in your head, or on paper, that's fine too, no judgment here, or look at your neighbor, no, don't do that. See if you can figure out what the velocity of that is. Calculate it yourself. What do you think the velocity is in centimeters per second? What is the velocity in centimeters? I think I wrote neat enough that you can tell. Okay. So we do like to use audience feedback in this class. We have a lot of weird ways that we do it, okay? I don't like to bring down polls everywhere every time it takes too long. I found a quick way to do it where nobody's embarrassed if they have the wrong answer. What I do is I count to 3, and then everybody at the same time says the answer, okay? So now I get a feel if everybody got it right, and you're not embarrassed for getting it wrong because nobody will hear you. Ready? So if you have your velocity in centimeters per second, I'll give you a 3 count, and then you say it. Ready? 1, 2, 3. No, you don't keep counting. You're supposed to give me the answer. Wait. Oh, 4. Oh, that's 4. Oh, okay. Very good. I think almost everybody said 4. Okay. If you didn't say 4, think about why. Think about what went wrong. Okay. So we'll do those. Just get used to that. It's not scary. You can do it. Okay. So this is a case of how people might be unhappy with this class, where we just talked about that, and we didn't show how to do a problem. So now we're going to show you where the formulas come from. Jeez, that lets you do a problem. These are the original 1914 boards, by the way. I'm not kidding. Okay, let's see. It makes me nervous when y'all laugh and I'm not looking. Like, I don't know what it's about. That really scares me. So now we're going to talk about how to do kinematics. How do you do the problems that you need to do? We just did some of this, right? We just had more analyze x, vt, and at graphs. We actually talked a little bit about the calculus of kinematics. You just don't know it yet, but you'll know it very soon. Okay. Okay, let's see. So how to do kinematics. And we're going to do the case of uniform motion with initial and final positions. With initial and final positions, x1 at t1 is the initial, and x2 at t2 is the final. Okay? So let's go back to our definition then. So I'm trying to show you that the definition is what you actually use the definition to do kinematics. So let's say our definition was that Vx equals x2. Oh shoot. Let's do initial final. Sorry, initial. It'll look nicer and match your expectations. All right. So x final minus x initial over t final minus t initial. That was just a definition of the slope, right? That's all that was. Okay. So now in some problem, though, you're asked, where does it end up? You know, a train leaves Bakersfield 3 o'clock going 80 miles an hour. When does it get to Tucson or whatever? So that kind of problem, you want to know where did it end up, or how long did it take to get there? So let's solve this for xf. X final. Oh, let's see. Oh, sorry. So we're going to bring this up here, and we're going to say Vx equals final time minus initial time. So all I did is bring that up here, and that equals x final minus x initial. Almost there, right? And then we're just going to bring this over here, and we're going to say x final equals, this is positive x initial, plus t Tf minus Ti times T times V. Tf minus Ti times Vx. The x subscript just means we're on the x-axis. So people tend to write that in one dimension. I don't know why. Okay, so that, but then usually, we don't really get into, usually you say that Tf minus Ti equals delta T. We rarely write it like that. So you might say that the final position equals the initial position plus Vx delta T. And that's kind of a standard way to see it in a book, right? Maybe that seems kind of familiar. I don't know. So I'm just showing you that that comes from the definition. It's not that we define velocity, then we have these special kinematics equations. The kinematics equations are the definition. It's the same thing. You're just rearranging stuff, right? Also, maybe you may have seen it like this. You're thinking, okay, that's what I saw in high school, but this delta thing, I don't know what that is. So maybe Ti equals 0. Then in that case, delta T, or then you could just say Tf, just call it T. Right? It's just T. You have to call it time follow. You assume everything started at 0, and after some time, where did it end up? So you could also write it xf equals xi plus vxt. There's no difference between these. This is kind of that context thing, right? If you're panicking about notation, you got to get used to notation changing a little bit, problem to problem, all right? There's also a street name for this, okay? The street name is xf minus xi is kind of how far it went. D, this is maybe what you memorized, right? D equals vt. Okay, some eyes lit up at d equals vt, yes? So remember d equals vt. So d is just the difference between the displacement. It's sort of the high school level word for displacement, xf minus xi, okay? So that's where those come from. And we're going to drive more of them. That's the straightforward one from the definition of velocity. When things start going different speeds, or when things speed up and slow down, it'll get more complicated. Right, so let's see. So that was a little bit of concepts and calculus of kinematics. You don't see the calculus yet, but it's coming. It's coming for you. Get ready. Okay, so now that we have that, we're going to do an actual problem together. Let's do one, just to show you exactly how to use this, right? Let's turn this down. I think I've got a problem keyed up here. There it is. So my wife's a pediatrician. I don't recommend you talk to her about medicine. You can if you want. And I'm kidding. She would love to talk to you about medicine. So she wrote this one, right? So you had a kid, sees a needle, and starts to run, right? 8 meters per second, goes down the hall in 3.5 seconds. How long is the hall? If you've had high school physics, you can probably do this one. So be thinking about it a little bit. And this is on our skills list. Let's see. One of our skills, I just acknowledge, is plug and chug constant acceleration. Although this is constant acceleration kinematics. This is plug and chug constant velocity kinematics. Right? This is really just d equals vt. But there's a few little things in here. If this one really stumps you, I want you to show you what's a little tricky about it. Okay? So one thing is, it never says velocity. It never says Vx equals, right? That's context. Oh, it's running at 8 meters per second. So we know that Vx equals 8 meters per second. It's also not real explicit about, well, he started at time equals 0, and he ended at time equals 3.5. Ti is 0, Tf is 3.5. You have to figure that out. You read this and you say, oh, delta T is 3.5 seconds. Okay. It's kind of obvious in this one, I think. But in more complicated problems, it won't be so obvious. I'm trying to show you that there are contextual things you have to get. Right? So here you know that delta T is 3.5 seconds. Okay. So then you could use your complicated formula, xf minus xi equals blah, blah, or you can just go straight for the throat and do the d equals vt. All right, how far did he run? D equals 8 meters per second times 3.5 seconds. I can almost do that in my head. Let's see, A16, 24 plus 4, 28. 28 meters. Okay. Hopefully that's what you would get if you did that problem. And then you'd say, how long is the hall? 28 meters. This is dead now. Or the computer frozen fast. That's not how long the hall is. That's how far the brat ran, right? If you think about it, you got to think about the context. What's really going on here? Did we measure the length of the hall? Did I say the brat started at the end of the hallway and ran to the other end? No, that's how far he ran, right? So you can also get context and find where you're not really sure what it's asking. So this was an ambiguous problem, technically. Although sometimes they are ambiguous and there's nothing you can do about it. Okay? So that is how to do a problem. There you go. Okay.